This mini session is on the CPU versus the GPU. We've been using both of them throughout the entire bootcamp, but this is just going to share a little bit more intuition of why the GPU is so much faster, as well as some of the other minor differences between these two pieces of hardware. Before we do that, there's this fun Mythbusters video of them illustrating it with paint cannons. So let's go ahead and watch that.
Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
And 10,
9,
9,
8,
7, 6, 5, 4, 3, 2, 1.
That kind of is a fun way of highlighting some of the major differences between GPUs and CPUs. As you saw, GPUs are composed of a lot of individual processing units that can all act in massive parallel, compute things in massively parallel amount of time. CPUs tend to be more discrete. They have to take one step at a time. It's very sequential in nature. But yeah, it's a fun way of doing that. So some of the high-level differences, the CPU is and has been the backbone of computing since really the 1970s. It's really made up most of the computing systems that we use because it is so flexible and so powerful. However, GPUs have been developed relatively recently-ish, still within probably the past 30 years. But they're mainly developed for visual rendering and things that require a lot of compute, but not necessarily super complex calculations. So it's really useful for like rendering videos and images, really useful for computer games and graphics. Another major difference, CPUs have, several complex cores, on an order of 10 or so. I think the most I've seen is like 128, maybe 64 CPU cores in a single machine. But each of them has memory for caching and rapid access. GPUs, however, have so many more cores, but they're very simple. So they have thousands of cores. But this allows them to act very, very quickly and be able to be massively parallel. And they all share a unified sense of memory. So there's a little bit of nuance with that too. The CPUs have been optimized for flexibility in performing these complex tasks, but in a sequential manner. So it's really good for like interoperability if you're like need to be interacting with the system and you're switching between tasks. It's really flexible and able to divert resources and processes towards different tasks. So pretty much like whenever you're using your computer, you're often running on the CPU because it is able to really handle the diversity of tasks you're interested in. So maybe you're like watching a video in one tab and typing something on your word processing in a different tab. However, GPUs are optimized to perform many simple but compute-intensive tasks all at once in parallel. But it comes at the cost of higher latency because there is some time it takes to transfer data to and from the GPU, which adds a little bit of latency. However, the CPU has a much lower latency. It's able to respond much quicker to your actions, allowing it to be more flexible. Questions about like the high-level overview differences? Cool. Okay, so these are kind of like a visualization of what a CPU looks like. There's this control unit that kind of receives your instructions and then figures out how to best allocate resources and like send them away to do the work you need to do. There's these arithmetic logic units that really perform the calculations themselves. So like the control unit will come up, if you like put in some instructions like, do some matrix multiplications, it'll figure out, okay, I need to do this, and then send the work over to the ALU that will perform that action, which will come back with the results. There's this cache, which allows it to be really flexible and store things that you're going to be using in memory, things that you're going to be needing frequently in memory. And then there's also a DRAM there for extra memory as well. When you look at a GPU, it's mostly comprised of these ALUs. So like we said, there's a lot of these different processors. They're much simpler than the CPU, but they all kind of have also a control unit, and they all share a lot of RAM. This, like you'll see, some GPUs have 16 gigs, some have like 64, but they're all kind of shared on the same system. There are some like nuances. You can start like combining multiple GPUs and kind of sharing memory and stuff like that, but that's too complicated for us right now. But yeah, so the control unit will allocate, will tell all the ALUs essentially what they're doing. There's a little control unit for each of these, but then yeah, it just performs all these things in massive parallel. That's really all I have for the lecture. I just wanted to share a high-level overview of why they're so much faster, but let's go through this Colab notebook that I created to help also illustrate some of the code differences and why things are also faster. So I created this little Colab notebook, and we'll be using it to do this demonstration. So we're going to go through some of the practical differences between the CPU and the GPU using Python and PyTorch. So let's first connect to our GPU. We're going to import torch and time. Torch allows us to really send things to the GPU, as Ben talked about a lot yesterday. And then time is just so we can do our timing estimates. So you want to make sure you have a GPU. It should, by default, use the T4, but if not, go to runtime here, and then change the runtime type to make sure it's the T4 GPU, if you don't have that by default. We'll run this just to make sure this says using GPU, or using CUDA, not CPU. Okay, we're going to create a function that we're going to use for timing our experiments. So here, we set the device to be the CPU, we start a timer, we run our function, we end the timer, and compute the time from the start and the end. Okay, so yeah, we do the calculation on the CPU, and then if we have the GPU, we'll do the same thing. So we'll move the device to the CUDA, to the GPU, start a timer, run the function, end the timer, and then calculate the difference in those times. So we're going to be performing a bunch of dot product calculations. This is just a very simple function to perform on vectors, but we're going to do it on various different sizes of vectors. So we're going to go from a size 10 all the way up to 5,000. And that's really to illustrate how powerful the GPU can be when you give it tons of data to work with. So I forgot to run this, so let's make sure to define that function. And then we'll define our list. So these functions here are going to be what we use to perform the dot product. The first of which is this very simple, naive way of doing it that uses a for loop for the computation. The second one will be a way of doing it in a vectorized way. I'll maybe explain a little bit of what that means. And then, I don't know why I said there's two, there's actually three. Yeah, there's three functions, and then the last one is using the built-in functions from Torch itself. So a little bit of explanation. This first function here is just getting a random tensor of certain size, but it puts it on the specific device that you're interested in. This for loop, so the dot product itself is you have two vectors of the same size. You simply just multiply each element by each other and then sum over all those. So we initialize our dot product variable to be 0. We loop over the first dimension of the tensor, and then for each of the elements in each of our tensors A and B, we multiply them and then start accumulating that for our dot product. A vectorized way, so this is a way of computing multiple things at once. It's still not like using the GPU, but it is using some efficiencies that people have created within the code base itself. So it's just like a faster, smarter way of performing calculations. Here, we can just take advantage of the vectorization that they've implemented for like the multiplication operation between two tensors. So here, this will perform an element-wise multiplication. So it'll do the same thing of every element in the tensor will be multiplied by every other element in the other tensor. And then we could do the sum, which will sum everything up in that tensor and create a single value that represents that sum. This final one is using the function in Torch itself. So Torch has a dot function, and we'll see what happens there. But this is actually a little bit more optimized, and then perform some back-end things to make it even more efficient. So we'll run that to define all our functions. And then for each of our tensors, we're going to loop over the different data sizes to create the tensors and then store all the timings for the different functions. So we'll go ahead and do that. Shouldn't take too long, 1 second. And now we're going to print the results. OK, cool. So as we kind of see, as the data size increases, the performance for the CPU mostly increases linearly. It takes, maybe this first one's a little slow, but like past that one, it increases more or less linearly with the dimension or with the size of the vector itself. This is kind of expected because it has to loop over every dimension of the vector, so it grows proportional to the vector size. The GPU, however, is actually slower than the CPU, which is maybe a little counterintuitive since I said, GPUs tend to be faster. But this is mainly because of the way we've implemented this function. It's very just not optimized for the GPU because GPU wants to handle a bunch of data all at once. But here we're telling it to do one thing at a time. So it's really just not taking advantage of the GPU's architecture itself. So it's actually much slower than the CPU. As we can see here, it's roughly 2 or 3 times slower. When we use the vectorized code, however, the CPU is much faster than it was with the for loop. So this kind of shows the differences between vectorization and naive for loops. This is important because it kind of leverages the low-level optimized code that they kind of built in with these tensors, which makes it really much faster. It grows less linearly with I mean, I don't know if this isn't linear, but it's still growing as you increase the size of the tensors, but yeah, it's no longer linear. When we do the GPU, now we're seeing some real benefits, especially once we get to these really large tensors that are 5,000 dimensions by 5,000 elements. However, an interesting point is when we have a small vector, the GPU is actually slower. That's because there is some overhead associated with moving the data to the GPU physically, and then it makes that computation and then moves it back. So there is a little bit of latency there that has to be dealt with. But past that, we see a much nicer speed up when we're using the GPU. When we use the built-in dot function from Torch, we see even more efficiency. The CPU also benefits from this. This is also faster. However, it still grows kind of with the dimension of the size of the tensors themselves. But for the GPU, we see even like it's still really fast, but it's like slightly more efficient than using the vectorized code. So I guess what this is really saying is if you can, please vectorize your code. That'll make everything more efficient. Avoid for loops if possible. Especially when working with these giant tensors that occupy a lot of memory and require computations across all the elements. And if there is a built-in function within like Torch itself, use that because it's going to have additional optimizations that are hidden kind of behind the scenes that allow it to be even faster. Yeah, so some of the takeaways that I list here, vectorization is really essential for the efficiency. It's much faster than using just naive for loops. There is a bit of overhead transferring the data to the GPU, so it could be slower for some small tasks. However, this is really, this doesn't matter for big tasks because of the parallelization of the GPU. It really, yeah, it makes this not a big issue anymore. And then PyTorch has really optimized a lot of functions. They have a lot of custom functions that are optimized behind the scenes that have some efficiency benefits. So if you have a function already implemented by like PyTorch, go ahead and use that rather than reinventing the wheel because they'll most likely be much more efficient.